the chances are extremely high that nobody here today or online hasn't flown in a Boeing 737 aircraft. The chances are also very high that maybe nobody has not flown on a Ryanair plane. Manueli did this morning. Ryanair, 3,600 flights a day, 230 airports from 37 countries, 610 Boeing 737 aircraft, 300 Boeing 737 MAX, due to join the fleet by 2034. 197 million passengers carried last year. For context, Lufthansa only 131, British Airways only 122 million. 27,000 employees, of which 7,000 are pilots. Therefore, it's my great pleasure, on behalf of the Royal Aeronautical Society, Berlin and Brandenburg Branch, which I need to say at this point, if you're a student online, you can join for free. If you're a Rolls-Royce employee, you can join. Rolls-Royce pays the subscriptions. You can follow us online via LinkedIn. I'm very pleased to welcome here today, on behalf of the Society and Rolls-Royce Deutschland, Christopher Coconnier.
Thank you very much.
So, after graduating with a master's degree in aerospace engineering from University of Bristol, Christopher joined Airbus Bristol, where he worked as a stress engineer. After that, he worked for Airbus in Hamburg on the A350 XWB program. Following that, he completed his commercial pilot's license in 2016 and joined Ryanair in 2017. Regardless of how often we've flown, I'm sure that you, like I still do, look into the cockpit door as you get off the plane and wonder what life is like at the sharp end of the plane. A 2024 study concluded that 80% of aircraft accidents have a human factor related cause. And despite the reliability of aircraft engines, the recovery from aircraft engine failures is still one of the most practiced aspects of pilot training. Christopher's very kindly agreed to come and present to us today his experience, benefiting greatly from his background both as an engineer and now a pilot, how the human factor component is inherent in upholding safety and future air safety. So, ladies and gentlemen, please give a big Dallas welcome to Christopher.
Yeah, thank you to you all. Thank you for coming here today, quite a lot of you. So let's jump in. I'm going to talk to you today about failure management, and it's my view as 737 pilots. Just quick disclaimer, this is not my company's view, but I'll just give my experience as a pilot and as an engineer. So we're going to talk about, failure, and of course, a lot of you here joining this presentation are Rolls-Royce engineers, so we're going to focus on engine failures. As Stuart mentioned, I wanted to add a part of this presentation talking about the human factors. It's a large part of aviation safety, and I wanted to bring it further so that we look at actually what does the future bring in terms of aviation safety. There's a lot of discussion nowadays about what's coming next with automation, with single pilot flight deck, and potentially autonomous aircraft. So let's jump in first, talking about engine failures. And let's talk about the training involved. So FATO is the name given for engine failure at takeoff. So why is this important? So originally, jet engines were, at the very beginning, quite unreliable, especially during takeoff phase when thrust would be engaged immediately, and failures used to happen statistically at higher rates during that critical phase of flight. So engine failure at takeoff was then the most practiced engine failure recovery in pilot training. And it starts from the commercial pilot's license. So basically, when I did mine, this is the point where, as a pilot, it's your first time in a twin-engine aircraft, and a twin propeller engine aircraft, and you spend most of your time with the instructor actually flying on only one engine. And why is that? Basically, the instructor spends most of the flights shutting down one or the other engine to see how you react. And basically, the immediate reaction you're supposed to have is compensate the yaw that you're getting from losing the engine and immediately stepping on the rudder pedal to compensate that yaw and apply opposite rudder. And that has to be ingrained from the get-go when we're flying twin engine aircraft. That's why it's so important. So generally, how does the training go? We do circuits, we're doing touch and goes, which means we're landing and taking off immediately. And just after the takeoff, the instructor will pick one of the engines, shut it down, simulating a failure, and we have to immediately react at opposite rudder, control the aircraft, and then deal with the failure. So, oh yeah, I've also got small asterisks here saying real engine failure. It was actually my only experience as a pilot with an actual engine failure was during my training. And as we were taking off, the instructor shuts down the right engine, and suddenly I look over my left and see black smoke coming out of the left engine. So immediately I had to reverse controls, add thrust on the working engine on the right, and then reverse the rudder controls. As we reduced the thrust on the smoking engine, the smoke subsided somewhat. Luckily, we didn't have any fire. Everything worked out fine. We elected to keep going back to base, and we landed safely. So then comes type rating. So for myself, it was 737-800 NG, and later on the MAX type rating. So all this training takes place in a simulator such as one of these. Some of them are fixed base. Those are fully moving simulators. And basically, FATO engine failure at takeoff is integral to that training. We also look at failures in cruise. We also look at failures on approach and practice these in the simulator over and over until we pass the type rating check. And indeed, the engine failure response is assessed during that check to get the type rating. And then further to that, then we're on the line, and flying on the line. You have this recurrent training. It's twice a year. As an airline pilot, we get thrown back into the simulator. And we get, so we have generally a 5-hour session in the simulator, and we get thrown at us all manners of failures, including, of course, engine failure, which is integral to those checks. We look at engine failure at takeoff, again, failures in cruise, failures on approach, and also sometimes we exercise more tricky things like dual engine failure and other survival exercises where we'll have a combined type of failure. And that is also, so that's twice a year, and once a year that is also assessed so that we get to revalidate our license. So our license is only valid 1 year, and we have to get reassessed every year to keep our license. Then, of course, there's flying every day with passengers. And engine failure, again, comes up. And it comes up as we're setting up the aircraft, we're planning our flights in the flight deck, and we have the moments of briefing with the captain and the first officer, and we discuss in that briefing the engine failure. So we discuss rejected takeoff, and we discuss engine failure at takeoff. And the way it looks like, it's basically scripted, a script we learn. And this is the captain's script, for example. So he'll call above 80 knots, I'll only reject takeoff for fire warning, engine failure, predictive wind shear warning, airplane is safe or unable to fly. So 80 knots is the speed threshold on the 737. where basically any sort of warning before that speed during the takeoff run that we get, any light flashing, any problem, we will reject the takeoff. Above 80 knots, we'll only reject the takeoff for those four things, including the engine failure. And then the next speed we're looking at is V1. Now, V1 is the speed of no return. That means at that speed, we basically have to make a decision to continue the takeoff, and we basically don't have enough runway at that point to reject the takeoff. So at V1, we have to continue. Just before that, we can still elect to stop the aircraft. So basically, this is scripted, and we say exactly those words to each other before every flight. And why is that? The reason for that, it basically arms our brain to do those actions. And in fact, a lot of us say the words and also do the actions. So these actions are basically pre-loaded in our brain in case something happens. Then the shock will first take place, and then we can immediately revert to an automatic response. And by the way, that's also the reason that you get, as a passenger, the cabin crew announcement safety demonstration, so that as a passenger, you get preloaded in your brain what you're supposed to do. So, in fact, that's why we even say for regular passengers, please listen, because you might be regular. It's important you listen so that your brain is preloaded with the actions you'll have to take. So we're going to have a look at flight deck indications. These are the first sort of how do we basically identify an engine failure. Flight deck indications. So this flight deck, the 737-800, we have in the center the engine indications, and then either side two screens each, one with the navigation display and one with the flight display. So below that, you've got the pedestal with the thrust levers, which looks like this. And just above that, I'm showing basically a couple of lights. So the indications that we get if there's an engine failure, first of all, we're looking out at the runway when we're taking off. If an engine failure occurs, we're looking out for where the aircraft is yawing. Immediately, we respond with pressing the rudder pedal to compensate the yaw. That's first indication. Generally, a failure will be associated with one or the other of those lights. So it's quite an old-fashioned system on the 737. The aircraft was developed in the 60s, and to maintain a common type rating, that system is still there today. So basically, on modern aircraft, or let's say more modern designs, such as the Airbus and later the 737, all failures are centralized on a central computer, which will basically tell the pilot, okay, this is the failure, and these are the steps you have to do to solve the failure. 737, we just get those lights, and we've got in red the fire warning and the master caution light. So in case of fire, the fire warning will come on. It's also associated with a fire bell, and then the response is quite clear. And master caution might relate to any of the lights that might come on the side there. Could be electrics, APU, fuel, and those come on just to give a general idea to pilots, where am I going to look at on the overhead panel? Which systems am I going to look at to look out for lights? Basically on the overhead panel and in front of us, each system on the 737 has an associated light bulb. When something goes wrong, that light bulb will come on and will tell you that system has failed. So very unlike more modern designs where everything's centralized on a computer, each system will have an associated light and tell us what has broken. Yeah, so let's have a look at the pedestal. We have the thrust levers here. We have the engine start levers below that, which basically ignite, inputs the fuel into the combustor. And we have the fire switches. So those are important in case the fire bell comes on. And immediately our eyes will go down to that and check which engine is affected. So those switches 1, APU, and 2 relate to engine 1, the port engine, the APU, and number 2 engine, which is the starboard engine. And those fire switches also have a light bulb, and they illuminate in case of fire. So we can't get it wrong. We can select the one that's illuminated. We pull it, that shuts down the engine, and then we can rotate it, and that will set off the extinguisher. So the 737, there's 2 extinguisher bottles, and for one engine, you can use one or both extinguishers if needed. So let's keep looking at flight deck indications. Fires are generally the easier ones to pick up. There are other failures, though, which are more common. Yeah, please.
Sorry, question. Do we actually have a feedback if the fire is extinguished?
Yes. So indeed the lights will extinguish once and we'll see first we'll also get feedback that the extinguisher bottle is discharged, and then the light will also extinguish for either overheat or the fire. Yeah. You're welcome. So yeah, in other cases we might not have a fire, and then it's a bit more tricky to identify what the failure is, and we have to look at the center screen where we have the engine indications. Those used to be gauges with needles, and they were updated with some digital indications that I'll show you in a couple of slides. It becomes quite relevant. And later on, they were displayed on the screen, such as this. So the way we identify it, so if you look on the far side, engine flame out will generally show the engine fail flag on the EGT. So for Rolls-Royce, that's the TGT. We've got the N1 indications and the N2 indications for the turbine. So on that side, we can see basically we've got engine 2 failure, no N1 rotation, but we do have N2 rotation, which means the turbine's still working. It's not a severe damage. So at that point, we can make the decision, okay, it's possible if we're in the right conditions that we relight the engine. On the picture to the left of that, if I'm facing it, basically we've got no indications at all on the engine number 2. We've got no N1 rotation, no EGT, and no N2 rotation. What that tells us, when there's everything blanked out, it's an engine separation. So the engine is separated from the wing, which is quite rare. We might have a case, for example, where we have still EGT and then no N2 indication. When that is the case, we generally suspect severe damage. I mean, the turbine is damaged. Another checklist we have to do. So talking about checklists, basically the way we respond to these is either we have what we call memory items, which means it's part of the checklist that we have to know from memory, and we do the actions immediately from memory. And the checklist looks like this. That's the quick reference handbook from the 737. And in there you have all the responses for all the failures. And that we carry around with us in the aircraft for all the flights. So, yeah, I'm going to carry on talking about flight deck indications and this case study, which is quite interesting. This was British Midland Airways flight 092 in the 1980s. 1989, it's brand new aircraft, 737-400. It was the re-engined 737 with the brand new CFM 56 engines. The aircraft, I think, was about 4 months old, and there was a fan blade flutter on the port engine and provoked uncontained engine rotor failure on the approach. And the pilots misdiagnosed the failure and shut down the other engine. Now, there's a few reasons for that, and we'll look into it. So one of the reasons, you see that was the updated engine indications panel before the screen digital display that I showed you before. This was the update. Pilots before that, by the way, both pilots were very experienced on the 737, but not experienced on this new aircraft. This display was basically an update where they digitalized information. They used to be just gauges, and the way pilots scan those is generally you have these bright white needles, and you could just give a quick look, and depending on the phase of flight, you could get very quickly have an idea that all the needles in the correct position and everything is going well. And if something is going wrong, you'll see the needle fall, something like that. So these new displays were already first source of confusion. Now, there was something else. There was not only a new engine design, but also new bleed air design. And they actually, in that engine failure, got smoke in the flight deck. And as far as they knew, on the 737 until now, the bleed air into the flight deck came from the right side, right engine. So when they had the smoke in the flight deck, they immediately assumed the right engine has failed, shut it down. Except this new design, 737-400, the whole concept was changed for the bleed air, and it was the other way around. The bleed air came from the left engine. And they hadn't received enough training or awareness from the company about this, so that knowledge was missing. Now, it's also important to note they were during approach, so the engines at that point are spooled down. A bit more tricky to notice which one is going wrong, especially on those new displays. On top of that, there was a distraction. So they got air traffic control calling them just at the moment where they were trying to diagnose which engine they were going to shut down. So I mentioned again here the lack of knowledge, the lack of training that came, which gave them this confirmation bias in selecting the right engine to shut down. There was also no communication with the cabin. The cabin, the pilots announced the passengers, we've got the right engine failure, when in fact it was the other. And the cabin crew noticed that actually that was wrong, but they didn't call the pilots, thinking they would be too busy, which was in some ways a correct decision. But at some point they should have called to make that known. It's also good practice for the pilots to communicate once they've done their checklists with the cabin crew to get any feedback from their side, and we'll look at that in a moment. So, conclusion of all this, both pilots were dismissed, and the court ruled pilot error. So we'll come back now on the quick reference handbook, just to give a bit more details. So QRH, as we call it, quick reference handbook, which is this. It contains basically all the responses to any kind of system failure on the aircraft. And that's the front cover here for you to see. And as you can see, a lot of the engine issues are on that front cover. Those are basically some of the main issues and the most immediate actions on the front cover. There are many more checklists in the actual book. And some of them you might notice are also written bigger, that's like the cabin altitude warning, or the evacuation, or the rapid depressurization. And that's because basically Boeing estimated in those conditions, you'll have limited visibility. And so it's written bigger because, for example, in the smoke, fire, fumes, or rapid depressurization, you suddenly get a lot of water vapor forming in the flight deck and in the cabin. So you want to be able to read that. So we've got here the engine fire, severe damage or separation checklist, same checklist, same response for both. And all those items, first 5 items, are memory items. So those are items we're going to do as pilots from memory. And we're basically going to call out all those steps. So auto throttle if engaged, disengage, thrust lever, engine number 1, confirm, close, engine start lever, engine number 1, confirm, cut off, engine fire switch, engine 1, confirm pull. Then if the fire switch is illuminated, rotate stop, hold for 1 second, and that basically causes the extinguisher to activate. So we have the list here of all the engine-related failures which have the checklist. So we've got aborted engine start also in the QRH, which is a failure on the ground, in which case we abort the starts. We've got engine fire, which we've mentioned, severe damage separation. We've also got surge or stall, which has a different, slightly different response, which we have here. We have engine overheat, which is basically EGT going out of limits without actual fire, and engine tailpipe fire, which might occur on the ground, and then also the more unlikely case, loss of thrust on both engines. And that, by the way, is the only time the checklist tells us by memory to attempt a relight, lost thrust on both engines. And in fact, we're going to later have a look at the relight. And most of the time, the checklist basically prompts us if we need to relight. If the checklist doesn't prompt us to relight, we don't do it unless it's double failure. So now looking at engine failure at takeoff, I'll bring you through the whole sequence because the checklist is only a very small part of what we're doing. So we're starting at the bottom here at V1. We're rotating and bang, engine failure. That's generally how we practice this in the simulator. It's generally statistically used to be the case when the worst case, when you'd have an engine failure at that point, you're going at high speed down the runway, you want to get out of the runway, you want to avoid obstacles. So you want to be able to climb out. So it's a critical phase of flight, and that's why we practice it. So after that, we call positive rate. So the pilot, in those situations, we always have one pilot flying and one pilot who's monitoring the instruments and doing the radios with air traffic control. And during a normal day, we interchangeably swap those roles with the captain and the first officer. So one is always pilot flying, the other one pilot monitoring. So in this case, in my company, we call pilot flying, we call positive rates. The captain will put the gear up. Of course, engine failure. So I'll be looking outside, apply rudder to compensate. Hold the rudder. Pilot monitoring will call air traffic control, call standby. So the reason for that is we don't want the air traffic control suddenly calling us and distracting us with any of the next things we're going to do. So when the air traffic control hears that, they know they shouldn't call us. 400 feet, we set heading select, we set a mode, and we call the pilot flying will call state malfunction. What does that mean? We're asking the other pilot to start analyzing what the problem is. We might have master caution lights. He's going to look at the N1, the EGT, the N2, the overheat, and the fire switches. And at this point, we'll call memory items, and we'll do the memory items. Then at the minimum flap retraction altitude, we'll call bug up. What does that mean? We're basically speeding up the aircraft. We want to gain speed and get a clean wing. So we're basically starting to reduce the rate of climb. And on one engine, we'll be as little as 100, 200 feet per minute at that point, which is not a lot. We'll retract the flaps, and that will enable us to gain speed. And after that, the flaps are up, no lights. We call the mode for the climb. We set max continuous thrust. At this point only, we can engage the autopilot. So for comparison, I have a few colleagues who've flown the Airbus. And on the Airbus at 400 feet, they can just immediately call autopilot. And that's it. During that whole phase, until 3,000 feet on a Boeing, we have to have our leg basically holding the rudder. And basically at that point, you start getting a cramp. So yeah, engage the autopilots. We climb to the minimum safe altitude. And at that point, we can take the foot off the rudder. At this point, the pilot monitoring can call HC and call either pan-pan call. And if it's more serious, in case of fire, you'd probably call a mayday call. So mayday, 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 your call sign, and then the failure. That's not the end of it. So we call ATC, we request a hold, or we request vectors to stay in the vicinity of the airport we've just taken off from. So at that point, the aircraft is under control. We have time now to look into the quick reference handbook. So we open up the right page and we go through all the checks. We read them out loud and do all the actions that are required. We come to a point when the checklist requires to switch the APU on to get a backup power source. We switch it on. While that's happening, we get the weather from the departure airport to see if we can actually land there. Possibly we took off with fog. That's those sort of conditions. We wouldn't be able to land in fog on one engine. We don't have category 3 landing capabilities on one engine because we don't have both autopilots in that situation. Then select the autopilot opposite the failed engine. And at that point, we can put the QRH on the glare shield and start planning to land at the nearest airport. At this point only, we do after takeoff checks, and then we discuss the captain and first officer about what we're going to do. Past discussion is calling the cabin crew and asking for any useful information, anything they've seen out of the window, any noises they might have heard. We then want to confirm a landing airport. So we try and get weather. If the departure airport's not good, we look at diversion airports, alternate airports. We then select one. We'll check the landing performance, of course. And by the way, on the 737, we're allowed to land with maximum takeoff weight, which is not the case on an aircraft in emergency. At that point, we've got a plan, we've determined where we're going. So we tell air traffic control, and then we tell the cabin crew. The pilot monitoring then enters the route in the flight computer, so we know where we're going to land back into the airport. And at that point only, then we do the public announcement to inform passengers we're going to land back at this airport, or we're going to divert due to technical problem. And then finally, we go back into the QRH Quick Reference Handbook, and there's a checklist for engine inoperative landing. So as you see, there's a lot to it. Basically, in the simulator, this whole procedure from the moment we have the engine failure takes between 40-50 minutes to complete. So that's quite a long time, considering you've got an engine failure. Of course, the aircraft are meant to be able to fly on one engine, so not a big issue. And we're basically taught to do this whole process at a steady pace and not give in to any sort of unnecessary stress, basically. So a quick word now on engine failures and cruise and the engine relights. This is more for the engineers here. Basically, how we determine we can relight. The checklist tells us basically when we can relight, except in the case, as I said, of a double engine failure, where we just immediately try it on memory. Just involves shutting down the engine start lever and then opening it again. And in the case the checklist tells us to do it, let's say after takeoff, we've got an engine flame out. We can attempt it, and you've got basically that flight envelope. So on the x-axis, you've got indicated airspeed, and the y-axis, you've got the pressure altitude. And generally at low altitudes, you'll be going around 220, 250 knots. So most of the time, you're in the area for the cross-bleed start. That means you're using the bleed air from the functioning engine to restart the failed engine. And if you're at higher altitudes, you can, as you descend, especially in the case of loss of both engines, you can reach much higher speeds. So above 300 knots generally, you can attempt a windmill start just using the speed of the aircraft and the wind to attempt to restart. That's it. And by the way, if we have a loss of thrust on both engines, what really interests us as pilots know where can we land. And one figure we generally have in mind is the glide ratio. And most airliners nowadays have very similar glide ratio, which is very good, I must say. It's about 3 nautical miles per 1,000 feet. So when we're in cruise, we're about 36, 38,000. Flight level 380, 38,000 feet. And that means we're basically looking at any airport within 90, 100 miles from our current position, which gladly in Europe gives a lot of choice. If you're over the Atlantic, less so. So that's just an example of the lost thrust in both engines checklist, and the memory items are the 4 first items of that checklist. And basically it's 2 attempts at relighting the engine. And the whole checklist basically gives multiple attempts at relighting the engine. Also gives indications of the flight level and the speeds required, if you look at point number 5. So we're now going to have a look at, yeah, please.
Questions. Do you try to stay at altitude if you have those engines out, or you want to dive down into the relight in the low?
Yeah, so if you try to attempt to stay at the altitude, you're going to stall because the speed's going to decrease, and so you're going to have to let the aircraft go down. So you'll call air traffic control with a mayday, and just say, yeah, we're going down.
You do to do your optimal gliding slope attention.
Yeah, that's a good question, and I've discussed this with Manuele quite a bit, and we don't actually learn about that as pilots, about keeping an optimal glide slope. We basically at that point, as the checklist points us towards, is getting the maximum speed possible so that we can attempt the windmill relight. That's it. Yeah. But it's actually the optimum glide is not something we have in mind. We have, well, let's say we don't have the optimum rate of descent. We just have, the idea that we can travel 3 miles per 1,000 feet just for landing purposes. So I'm going to show you now a video from our training department, which is basically a demonstration of the rejected takeoff. So you get an idea of what's happening in the flight deck and the pace of all the actions during an engine failure at takeoff. So I'm going to start that here, and I'll let you watch this.
Stabilized.
Set takeoff thrust.
Takeoff thrust set, indications normal. Eighty knots.
Check.
Stop.
Speed brakes up. 100 knots. Reverse is normal. 80 knots. 60 knots. Auto brake disarm. Mayday, mayday, mayday. Ryanair 1 Alpha Mike, fire, stopping on the runway, standby.
State malfunction.
Engine fire, engine number 2.
I agree. Memory items, engine, fire, severe damage or separation, engine number 2.
Auto throttle, if engaged, disengage.
Disengage.
Thrust lever, engine number 2, confirm close.
Confirm closed.
Engine start lever, engine number 2, confirm cut off.
Confirm.
Cut off. Engine fire switch, engine number 2, confirm pull.
Confirm.
Pull. Rotate to the stop and hold for 1 second. Left bottle discharge.
Okay, so we've still got the fire warning.
There's a lot of black smoke on the right hand side of the aircraft as well.
Okay, so then the safest course of action is to evacuate the aircraft.
I agree.
Okay, QRH evacuation checklist.
QRH evacuation checklist. Condition. Evacuation is needed.
I agree.
Parking brake set.
Set.
Speed brake lever down.
Down.
Flap lever 40. 40. Pressurization mode selector, manual. Outflow valve switch, hold in open until the outflow valve indication shows fully open to depressurize the airplane. Fully open. If time allows, verify the flaps are 40 before the engine start levers are moved to cutoff.
40.
Engine start levers both cut off.
Cut off.
Advise the cabin to evacuate.
This is an emergency. Evacuate the aircraft using all available exits. This is an emergency. Evacuate the aircraft using all available exits.
Advise ATC. Ryanair 1 Alpha Mike evacuating on the runway. I say again, evacuating on the runway. Engine and APU fire switches all override and pull. Override and pull. If an engine or APU fire warning is observed or indicated, illuminated fire switch, rotate to the stop and hold for 1 second. Rotated, right bottle discharge, evacuation checklist complete.
Okay, doors are open. If you take the lid, I'll pull the CVR-CV.
Sounds good.
Okay. So you see that's quite a lot. That's a long procedure when you have a huge fire like this particular occasion, which was American Airlines. So you can imagine the passengers in the cabin at this point. All they want to do is jump out of the aircraft. So we'll have a look, but there's a good reason why we go through this process, and you'll see it right now. Yeah, just get the sound there. So basically, this was in October 28th, 2016. It was 767 aircraft, so larger than 737. Operating flight was American Airlines, suffered engine fire during takeoff, and the crew aborted the takeoff. They managed to evacuate everyone on board. Evacuation aircraft certified to evacuate everyone in 90 seconds, so a minute and a half. And they had 21 occupants who were injured during this evacuation. So you can see now, front slide was deployed. The overwing slide is failing too. The aft slide. Can you see what's going on? Oh, try. Exactly. It was basically flying, and it wasn't due to the wind. Any idea what happens? Yeah, the right engine was still running. Exactly. The right engine was still running, and because you saw how long that process took. It takes about a minute and a half from the moment you get the fire indication, the fire bell, to do all those checks. Yeah, please.
In the first training video, there was like smoke on the right side. Was there any decision making in terms of we're going to evacuate on one side rather than the second side, or is it?
Yeah, absolutely. So basically, the cabin crew are trained at that point to look out the window. And by the way, that's why we ask all passengers before landing to open the shutters on the windows so that they can also see outside, and the cabin crew can immediately see outside. And in that case, we'll only evacuate on the other side. Yeah, absolutely. Yeah. So you can see. Yeah.
Sorry, just to pick up on what his question.
Yeah.
I think the call the pilot made was evacuate all available exits.
Yeah, exactly.
So then picking up on Ollie's question, your answer, the expectation is that the cabin crew will know which side the fire is.
Exactly. They have to look out, and they have to know which exit is available and not available. Exactly. They're trained to look out for that.
So they decide.
Yeah, I mean, they're trained to pick the right side. Absolutely. Yeah. So of course, in this case, passengers under the stress, they pushed the cabin crews on the American Airlines flight to open the door too early, and that was one source of the injuries. Basically, passengers trying to jump on the slide that was being blown into the.
You just mentioned the right-hand engine was blowing this, but it wasn't left.
Oh, the left. Sorry, yeah, I confused it. Yeah. It was the left that was still on and not shut down yet. You can see the engine start levers both cut off. Only comes, the seventh item. and then 8th item, advise cabin to evacuate. So yeah, there's a reason for that. We need to do things in order. Otherwise, mistakes are made, and potentially you can make the situation worse with evacuating if all those steps are not done properly. So that brings us basically talk about the human factor. And why is that? Hopefully what I've spoken to you about gives you a sense of the workload involved with dealing with those failures. And that workload is very high, and there's a lot of discussion in the industry right now to say, well, let's automate it, let's have single pilot from the flight deck. And there's that number that's bandied around since a few years in the industry, 80%. Any of you ideas what that number is regarding human factors and accidents? Well, Google says human mistakes contribute to about 80% of aviation accidents. Well, if we actually look at the published accidents, that's debatable. But more importantly, we'll have a look at what do they mean by human mistakes? What do we mean by human mistakes? And in my experience, in fact, I've also heard pilots say, well, pilots are responsible for 80% of accidents, confusing what this human factors actually refers to. So let's actually look at all the humans involved in the whole ecosystem of aviation, starting very much from the beginning, on the left side, the design phase, all the way to the operations phase, where we're taking passengers from A to B and landing safely. And we've got stress engineers, design engineers, software engineers. We've got the testing, we've got certification, and further. So basically at each of these steps, believe it or not, even in my experience at Airbus as an engineer, we have made mistakes, we have forgotten things. 737 MAX showed that certification mistakes have also been made. Then we've got the manufacturing. There it's quite usual. Fitters, machinery, inspection, non-conformities. These things happen regularly. Then further on towards the operations, we get the maintenance, A, B, and C checks. Not unusual in those conditions. They go stripping the aircraft, parts are missed, sometimes tools are left in the wing tanks. These things have happened. We then got our B1 engineers. After a long day flying, the B1 engineers come to check the aircraft every day during night time, checking the aircraft. Tools might be left in the wheel well. These things have happened. Then on the operations side, finally, we've got the pilots, cabin crew, ground staff, passengers. Can't forget the passengers, also a very big human element on passenger flying. Sometimes they do things that are unpredictable. Sometimes they fall ill. In the worst case, they try and do something deliberately to bring the aircraft down, which is rarer, thankfully. And then, of course, we've got the air traffic controllers who work hand in hand with the pilots. These two cannot be dissociated. And some of you might have seen this model called the Swiss cheese model. So every stage, every person here working and highly trained person constitutes a barrier to any problem. And when a mistake is made, you basically get a hole in cheese. And some days, these holes unfortunately line up and you get a safety incident or worse, an accident. And we've seen in the previous examples that it's never just one issue that causes an accident. It's a succession of problems, generally something that went wrong with the design, something failed, it wasn't managed properly, etc. And then we have an accident. And in the industry today, some are saying, well, let's just take this human out of the equation, the pilots, and it will solve 80% of the accidents. Well, we can think about it. This is an example, Qantas Flight 32. where the pilots actually did a great job. So crew coordination was excellent. This was 4th November 2010, Qantas flight flying from Singapore to Australia, and they suffered uncontained failure in one of its 4 Rolls-Royce Trent 900 engines as they were climbing towards cruise. The crew coordination was great. They assessed the damage they went through. So it was an Airbus, so they didn't have this book. They had all the failures centrally organized on the flight computer, the ECAM. And basically the good thing with that is it also prioritizes the response. And especially important in this case, where we had multiple failures. It wasn't just the engine, but the engine also split the front spar. So there's a fuel leak, there's hydraulic lines that were broken, extremely complex. It took them 50 minutes just to resolve all those issues on the ECAM. And then only after that, they could try and see where they could land. They selected to go back to departure. The weather, thankfully, was good. And the performance was just good enough for them to land full of fuel, of course, very heavy. They took a hold. So this was captain's initiative, not written in the books. They decided to take a hold next to the airport to allow them to also burn more fuel and to try the flaps. They could see how much flaps they could actually get. And they also gravity dropped the landing gear because obviously they were lacking hydraulics at that point. And they landed safely. They landed. There was still a fuel leak. And the emergency services arrived. The captain then made a very important decision. He elected to keep all the passengers on board. One of the engines wouldn't shut down. Basically, they tried to shut down and it kept running. So they basically the fire service had to extinguish it from outside. And that was with hundreds of passengers on board. It turned out to be the right choice. Now, I was working at Airbus during those days and actually on the A380 team for a short while. And we got the return information. The wing was completely dissected in detail after this incident. We were checking everything. And what we discovered was very surprising. This was a new design of a wing. We basically had ribs with a web made of carbon fiber and aluminium feet. It turned out we found hairline cracks on the aluminium feet, signs of early fatigue. Now, this was not expected. So basically, the feet of the ribs had been designed wrong. We'd chosen the wrong aluminium alloy. Luckily, we didn't have to ground the world fleet of A380s for that. At that point, when that accident happened, the world fleet was young enough that we could just bring the aircraft back in maintenance and make the necessary changes to all the rib feet of all the A380s in the world. So quite a massive design flaw, and that incident basically allowed us to discover that flaw thanks to the pilot who saved the day. So we go back to our Swiss cheese model, human mistake at the very early design stage, saved at the end by the pilot, and eventually solved by the engineers. So we can quantify how often pilots got it wrong, very easily done. How do we quantify when pilots fix a problem? A lot more difficult. It's happened to me in my career, and it happens weekly. Small things happen, small mistakes are made by air traffic control, somebody on the ground, small technical failures that don't seem big, but we just solve them as our daily operations require. And yeah, we need to think also, it's not just the pilots involved, there's humans all around. Yeah.
So when you discover something, what is actually the feedback mechanism?
Yeah, so if it's serious enough and we can't fix it, we have what's called a technical log, and we'll write it down, and then as soon as we land, we'll call up the engineers and ask them to fix it, basically.
It's more thinking like you discover something that you think is a generic problem.
Oh, generic problem.
Yeah.
Okay, well. Yeah, that's a good point because yeah, we can talk about that maybe. If you keep that in mind for the question time, we can discuss that point. It gets a bit more tricky. Yeah. Yeah, please.
About human factors, you called out for ATC communication. Just recently, when this air collision happened, there seemed to have been overlay when the air traffic control was talking, the pilot was also talking on the same frequency, and they couldn't hear each other.
Yeah, you're referring to the one in Washington, the Black Hawk. Yeah, yeah.
I'm just wondering, what is the reason why we can't have a frequency where everyone can hear the other one while they were speaking, and then you can also notice that somebody is talking over somebody.
So generally that's correct. If multiple calls come in together, then you basically get a garbled sound on the radio, and you don't really hear what's going on. Some air traffic controllers are equipped with a system where they can hear simultaneously what's going on. Aircraft are not, as far as I know. And it's a point where the technology, I'm not so familiar what's actually the why, as you say, the aircraft can't overhear. The reason is, I think, as soon as you hear garbled, it prompts the pilots to let go off the mic so that they just let silence and then somebody come in. And so I think that's why it was deemed that the technology isn't required in the flight deck and used just on the ground so that actually, as you say, the air traffic control could hear both. But it's not at all airports or all control stations, as far as I know, don't have this this technology. So, yeah. So which future do we choose? So some of you might recognize this 2001 Space Odyssey, where the computer takes over the spacecraft and stops its crew that's doing a spacewalk from coming back in to the spacecraft. Or we've got this. So we've got two-man crew. This is in the Dragon SpaceX launcher. We've got a two-man crew. These guys spent months training for that flight. They came back from that first flight and said they had nothing to do. But yet they trained for everything possible that could have happened. And they were two on board of this flight. You might also notice that one of them is wearing an analog watch. He's holding a pencil with a piece of paper. And why is that? So remember Swiss cheese model, the barriers. All these things are important to keep a barrier in case something fails. So talking about single pilot, autonomous flying, those who are less familiar with the industry immediately say, well, the technology is there, we can do it, there's no problem. The only thing stopping us is passenger acceptance. Well, I would say those people are being disingenuous. They're basically trying to stop the real discussion about the real problems that we're going to come into in a minute. So passenger acceptance, widely publicized as the only obstacle, we're going to see that it isn't. One of the main obstacles in my view, so let's say you're an airline, suddenly Airbus, Boeing comes up with the first fully single pilot aircraft. By the way, what I'm going to talk about here is not what Airbus is calling single pilot flight deck at the moment. At the moment, Airbus for the A350 only is talking about single pilot flight deck on long haul flights only. And what that means is instead of having 3 or 4 man crews, they'll reduce it to 2 or 3 man crews. So there'll be phases of flight during the cruise, but there'll only be one person in the flight deck. And discussing with friends who are in long haul, already that they think is taking it too far. Why is that? Because of course, if 2 crews are asleep, something happens, they have to run in the flight deck. It takes time to get your brains working again, awake, and to get the efficient response time. Still, that's what's being proposed by Airbus. What I'm talking about here is going further. It's something that is being put which would be just a single pilot for the whole operation. So we've seen with the engine failures, the workload involved, etc. You're an airline, you've got this new aircraft that's single pilot flying. So you say, great, I can get rid of half my crews. I've got all these experienced captains, perfect, they can fly the aircraft. And then they retire. What happens? How do we train that next generation? Not going to do it in simulator. Simulator is such a small part in the type rating of what you're learning. The moment I went from the type rating, I thought, wow, I can fly this aircraft, great. The first day I was in the aircraft ground training, flying the aircraft empty. Air traffic control calls, and my hand sort of hesitates, should I touch this aircraft? And I was sat next to extremely experienced training instructor, captain, who said, go ahead, just do it. He put me at ease. And then there's the next step, you're flying with passengers. And it takes a lot of time to accommodate. It then takes a lot of experience to actually get the exposure to any problems. And today, thankfully, aircraft and engines are extremely safe, which means, in fact, we get less exposed than previously dealing with issues. So we really get, in those 3,000 hours that are the bare minimum required to upgrade as captain, we get less exposure to problems as there may previously have been. So in practice, airlines actually require first officers maybe spend 10 years on the right seat before upgrading. That's how much experience you actually, and in airlines, talking with captains, they often say, well, you get confidence after 1,000 hours, but it's the bad confidence. Confidence where you think you've got under control. And actually, then there's another step. Actually, something happens and you realize, whoa, okay, actually, I don't have this. So, and in fact, captains, there's also continuous learning. They're always learning throughout their career. There's always something that will come up and they'll think, wow, I've never seen this in my whole career. So some will say, quoting that previous number, 80% accidents, human caused. Well, it's clearly safety related. Put less humans in the flight deck. We're solving a safety issue. Well, we know from experience within our pilot training that over-reliance on automation is problematic. In fact, the airlines promote us to disconnect the autopilot as much as possible when the conditions require, so that we get manual handling of the aircraft and practice. Good captains will also nudge their first officers to also disconnect and fly regularly by hand, just to keep that skill alive. And yeah, you can't replace that. We also know from our own training, from human factors training, that humans intrinsically are extremely bad at monitoring automation, monitoring screens. We will fall asleep, we'll get bored, and we'll just get startled when something happens. So what does single pilot cockpit actually mean in that sense? It actually means that for it to work, you need an aircraft that does everything on its own, even in case of failure. Because the day something happens and there's that single pilot, he'll be so overloaded with work, he will not be able to respond. So the only way is either 2 crew or no crew. And then there's the question of insurance. So we've seen previous examples where previously in history, it was very quick, very easy to just say, oh, we've got a crash, pilot error. Pilot error, sweep all the issues under the rug, and then the manufacturers will slowly fix the problem behind the headlines, behind closed doors. It's also a point Emanuele brought to me saying that for space launches, insurance for new space launches is actually extremely expensive, because they don't have the data, they don't have reliability data to basically assess how expensive it's going to be. So quite a problem for the new space launches. Could potentially be the same for aircraft insurance if we go that way. And then finally, I'm going to touch word on 737 MAX accidents because it's quite relevant, and we'll see why. Again, so just briefly, by the way, there was a very good Royal Aeronautical Society lecture discussing this. It was just a couple of months ago. I really recommend you watch this. Pilots and engineer, I believe, discuss this topic really in depth. So I'm not going to talk about it in depth, but just touch words. So just to remind you, there was a Lion Air flight on October 29th, 2018. First crash, first Boeing response was pilot error. Lion Air didn't do their job properly. Unfortunately, and sadly, it was 6 months later about Ethiopian Airlines, same crash occurred. So we have multiple factors: new engine design, new software, the MCAS, inadequate sensor redundancy, omitted pilot training, sensor failure, distractions during the failure, pilot response. You see any pattern? Same thing as the British Midlands flight. Similar things, multiple new engine, new software, etc. Boeing eventually took the blame. Direct costs were estimated $20 billion. Indirect costs nowadays are estimated up to $60 billion. Because of that, Boeing has now reduced their rate of building and delivery for the 737 to around 5 to 10 a month when they were previously over 45, 50 a month before those accidents, because the FAA is right behind their backs, breathing down their necks, checking everything. So there's a good saying in English, which is penny wise, pound foolish. Thank you very much for listening. Thank you.
We can start with the audience.